to go live now. All right, welcome back. We are Game 2005 in the fall 2021 semester at George Brown, and it's Game Physics, and it's week 5, part 1 of our broadcast. You may have another broadcast via Joss and his tutorials this week. And this week we're going to be talking about circular motion. So first I wanted to welcome everybody back to this one. And let's take a look, like we always do, at our schedule. So we're sitting at week 5. Last week we talked about the laws of motion. So Newtonian physics, we started talking about that. That was, we also, you had, most of you had submitted assignment 1 on time on Friday. Some people did not. That's okay. And assignment 2 was released, okay, and that is due next week on next Friday, so that's when it's due. So we'll talk about that in a bit. And so we're doing circular motion now, and then finally energy of a system next week, followed by your midterm test. Let's talk about that really briefly. So again, this week, circular motion, which is building on the stuff that we talked about last week with Newtonian physics. One thing to note and reminder is that next week, Thanksgiving is on Monday. So some people who are celebrating, or even if you're not, you're off from school. There's no school on Monday. So if you have another course that you're taking on Mondays, either the makeup time has already been made up for you, or there's a recording or something else that's going on for that course that's normally scheduled for Mondays, but you won't be coming into class on Mondays, that's for sure. It comes to next week. So next week is a shortened week. So keep that in mind when you're working with your teams. Again, assignment 2, which is a group assignment, is due next Friday at midnight. And again, please know that you cannot continue working on your assignment with your earlier group. So if you're still in A1 group and you haven't joined an A2 group, you need to do that. I've made different groups, and I'm going to continue to make new groups every single time we have an assignment to give you a chance to work with other people. Good morning, Neil, and Miguel, and everybody else. And so that it gives you a chance to change groups if you need to, or stay in the same groups, but you need to continue to, no, you can absolutely stay with the same partner, but you just need to change groups. So you have to subscribe again to a new group or join a new group on A2 groups to give you a chance to both work together. Both of you have to, of course, agree to join that group again. So please, I know it's a bit of administration, but you need to join another group. A2 groups is coming up for this week. So please do that. All right, upcoming. I also want to mention that the midterm test is imminent. It's coming up not next week, but the week after. It's a true-false multiple choice Blackboard test. You'll have multiple attempts to get it done, just like normal. You'll have the entire week to complete it. As an example, it'll be released on early in the week on a Monday, and it'll be due at the end of the week on let's say the Friday of week 7. So that's not next week, but the week after. And there will be no lectures during week 7. So give you a chance during this time frame to complete your test. If you don't have any other time during the week, they have a chance to do it. I'll also be here during week 7, not to produce a lecture, but actually to answer any questions you might have related to the midterm test, and to reset you if you have a technical issue. Okay, so that's what I'm doing. Okay, so Lyra says, you accidentally joined a group with others. Can you remove me from 15? Yes, I can. 1 second. Let me just do that now while we're going. I'll just go into and do that offline. We can do this. So Lyra, you have been removed. You're good to go. Okay. Neil says, for assignment 2, do we treat the object like a simple point in the center? Yes. So you're treating it like, again, we're going to create a free body diagram, and you're treating the object as a particle, for sure. Okay, any other questions before we move on to the meat and bones of what we're going to be talking about today? Just wanted to kind of go through this with you to make sure that everyone is on track. Person. Time. 1 second. Okay, so do we have no labs next week? I don't believe there's. I'm not sure if Joss is going to produce a lab next week or not. I would recommend checking with him. But again, next week, if you have a lab on, if you're scheduled to be on a lab on a Monday, then I'm not sure what Joss is doing, if he's going to record something on another day for you or something else like that. But the following week, also check with him, because he may or elect or may not, to produce a lab for your, during your exam week. I doubt it. So just check with him for the next 2 weeks, because he's going to be the one that's going to kind of, he's directing those things. All right, so let's continue with what we're talking about today, and I'll come back to administration for anyone else that needs to move out of a group or whatever. I want to make sure that you guys are good. So again, we're talking about circular motion and other applications of Newton's laws today. We have 43 slides to go through. We may not take us the entire time. We'll see how it goes. I know I keep saying that all the time, but we'll see how it goes. So again, we've kind of been using two analysis models for Newton's laws, right? And so far, what we've done is we've been applying the models to linear motion. Okay, so Newton's laws also can be applied to other situations. We can apply it to circular paths. We can also apply it to motion observed from an accelerating frame of reference. And we can also do it with motion of an object through a viscous medium. Okay. And this part, accelerating frame of reference, chances are we're not going to be talking about that here, because, again, that would be real physics that we're working on. We're working on game physics. Viscous medium, that can mean a lot of stuff. That can mean a liquid or a fluid. That could also mean air. All right. So that is also something that we can think about. That may or may not come into play when it comes to game development for us, right? Let's think about some of this stuff. So one thing that we're going to be talking about is this idea of uniform circular motion. We kind of talked about that last week, where we said a particle moves with a constant rate of speed in a circular path of radius r, right, as an example, with some kind of acceleration. And the magnitude of the acceleration is given by this thing we talked about last week, really briefly at the end, which is centripetal acceleration, right, is equal to v squared over r. So the velocity or the speed over the radius. All right. And what we're thinking about, again, like we talked about last week, is the centripetal acceleration is directed towards the center of the circle. All right. And that's where the energy is going, towards the center of the circle. The centripetal acceleration is always perpendicular to the velocity. So this is just a review of kind of what we've talked about last week. And there's no change in the speed, only in the direction. Okay, so that's kind of the thing that we're talking about as well. So when we look at the diagram that is related to this, a force F is associated with the centripetal acceleration. So the force is kind of pointed toward the center, right? And you can see that there is a radius r from the center of the circle outwards, all right? And applying Newton's second law, where force is equal to mass times acceleration. Hey, wait, let's do the other things. Can anyone remember from last week, what are the three laws other than F is equal to ma? What's Newton's first law of motion? Don't look it up. Can someone kind of type it in or come on the mic and say it? If you want to come on, I'll take the first taker who wants to come on the mic, or someone who wants to just tell me what it is, right? Okay, Sean's the winner. He's come up instead of first. An object at rest, an object in motion will stay in motion. That's important. But what about the second part, the object at rest part? That's also part of the second part, unless acted upon by a force or something like that. Yes, but we can simplify the first law of motion and say an object at rest tends to stay at rest. An object in motion tends to stay in motion. That's the first law. Second law is force is equal to ma. We talked about that. What's the third law? This is key for your other things we're talking about this semester. Third law of motion. What is it? Can you simplify it and talk about it in a very succinct manner? Okay, Neil says equal and opposite reactions. Okay, pretty good. For every action, there's an equal and opposite reaction. I think that's the way I'd like to think about it. Sophia kind of summed it up as well, and so did Nihar. I think it's an important thing because basically what we're talking about is that is our collision detection and response. For every action, there's an equal and opposite reaction. Equal and opposite, which means it comes back at you, depending on the mass that's used. So here we're talking about force equal to ma. This is the Newton's second law and how it works with circular motion and where the force is directed. A force, right, causing a centripetal acceleration acts towards the center of the circle. This is what we just talked about. And it causes a change in the direction of the velocity vector. So notice the velocity vector is this way, then it's the velocity vector this way. If the force vanishes, then what happens is the object would move in a straight line path tangent to the circle. So in other words, let's say, for example, the string or the rope that's tethering this object, the puck or whatever this is, to the circle, if it breaks, then what happens is the puck becomes untethered and leaves the circular path in the direction of the velocity vector. Okay, that's what happens. So that's the one thing that you're going to see. It's going to be tangent to the circle in the path that it left. All right, so one also thing we can talk about when it comes to circular motion is this idea of a conical pendulum, right? So a conical pendulum means something that's connected at the top, as an example, or a tethered to the top, let's say, of a ceiling or the top part of a system, okay? And then a pendulum where it swings around in a circular motion, right? But it's tethered at the top, right? And conical because it makes a cone shape with its motion. So that's what a conical pendulum is. Something where we have a mass that swings around in a circular motion, right, around a tethered point that's tethered above, the actual object, right, at some length. So notice we have a length L, we have an angle theta, and we have a tension T that's going towards the tether, right, and then you have a mass mg, right, or a force mg, which is mass times gravity, that's pulling us down. So those are the things. We also have the radius, which is also another measure. These are all things we know, okay? When it comes to decomposing our forces, we know that the force upwards, if I want to decompose the tension force or the tensile force, we know that the force upwards is T cos theta. There's that cos related to the y-axis again, which is interesting. This is the opposite of what we talked about. Remember, anything that seems to come at an angle, it looks like our relationship with cos and sine on the axes that we talked about before. For example, cos is normally aligned with the x-axis, sine is normally aligned with the y-axis. Well, that's flipped, as an example, when it comes to this scenario, as well as any slopes that we might see. So again, we notice the sum of all forces across the y-axis, this is how you would read that, is equal to 0, right? And therefore, we can say that it's the tensile force cos theta is equal to the mass times gravity. Why is it 0? Because we don't have an upward or downward motion. We only have a motion around the x-axis, around the horizontal. And this is where we say that the sum of all forces across the x-axis is T sine theta. So we take that angle theta where the object, the pendulum, is actually hanging. And that's equal to mass times acceleration, or centripetal acceleration is what we want to say. The energy that's going towards the center of the circle, right? And then when we know this is centripetal acceleration, we can break this down a little differently. When we kind of revamp or massage the equation, so mass times centripetal acceleration, if we go back up one to see what centripetal acceleration is, that was way back up here, we know that centripetal acceleration is v squared over r. So we can say that centripetal acceleration, if it's mass times ma, right, it's mass times mv squared over r. That's what it becomes. Mv squared over r is what the new equation becomes. mv squared over r. So once we have mv squared over r, when we move things around, we can say that v is independent of mass, right? That's one thing. We don't care about the velocity. Mass and the velocity have no, there's nothing to do with it. We can say that velocity is, you take the square root of the length of the rope from the tether, all right, multiplied by gravity, and then sine theta, tan theta. We found that this equation really gives us a sense of what the speed is around the circle, if you will. So the velocity that we're getting. Motion in a horizontal circle. So the speed of which the object moves depends on the mass of the object and the tension in the cord, right? So the centripetal force is supplied by the tension. So the more tension there is, as an example, it really depends on the mass. And the maximum speed, if we ever wanted to find the maximum speed, that corresponds to the maximum tension that the string can withstand. All right, so try this at home. Take your tether a ball. Maybe not try this at home. Try this outside. Try it outside. Don't try it at home, or you might smash something. Take a ball or some kind of sling and swing it around, below you as fast as possible. So not above your head, but actually kind of make your wrist act like the tether, and swing the ball around in a circular pattern as fast as you can. And you're going to notice that the tension that's on the cord or whatever is tethering to your hand, right, becomes more and more until, if you go fast enough, the cord will snap, and because you've exceeded the maximum tensile strength that's associated with the cord. Why? Because remember, an object in motion tends to stay in motion. So this is Newton's first law, right? Which is basically saying that it's going to go in the same direction. If you let it go, it's going to keep going in that direction, right? So it's not going to change directions unless I apply a force to it to make it change direction. So the way a sling works then, if I had a slingshot, the old slingers back in the day, they would take a rock and they would put it inside of some kind of, a handkerchief or something else like that, or some kind of an area that they would, some kind of springy material, right? A cloth or whatever. You would swing it around, and then you gather momentum. So you kind of increase the speed. And then when you let it go, the object has been accelerated to the maximum speed that it can go. And then when you let it go, it's going to continue in its path because there's no other motion or no other force being directed at it. It's going to keep going in the direction it's going until it hits whatever the target is that it's going to hit. So that's how kind of some kind of sling works. And the same thing when it comes to maximum speed. It's going to be based on the maximum tensile strength of the object of your cord or your tether. All right. All right. So here's another scenario. So that's the first scenario. So the first scenario that we're going to see, and you're going to see this conical pendulum thing will come up as a potential question in your midterm test, right? Because we're covering it here, and I'm giving you a couple of equations to help you. Okay. Here's the other scenario. Another scenario is when I have a horizontal flat curve and I'm being tethered, but what am I being tethered by? Static friction. So my tires on the road, right, as I'm going around a curve, is the thing that's keeping the car on the road, all right? So again, the force of static friction, we can say that it's pointing inward. Centripetal acceleration is going to be based on is the amount of force superseding or going over the force of static friction. Can I overcome the force of static frictions with my tires? If I do, guess what's going to happen? The car is going to fly off the road. So this is a perfect model for what happens in a scenario where I have a curve with no bank, right? Notice we're going to talk about banked curves in a bit. But if I'm in a curve with no bank, that means it's just completely flat. Then there's a risk if the force of static friction drops, example, ice roads or slippery roads because of rain, that my car or the vehicle that's on this road will swing off the road into oblivion, right? And why? Because the amount of speed, The maximum speed at which the car can negotiate the curve is based on this equation right here, which is the maximum speed is equal to the square root of the coefficient of static friction times gravity times the radius of this curve, right? So this is important. We can also break down a car into using the particle model and draw a free body diagram like this, where we say that the normal force is equivalent to the mass times gravity, right? So that's holding it up. But the force of static friction is the thing that's keeping the car on the road, okay? So what happens when we have a banked curve? Well, a banked curve actually improves our ability to stick to the road, right? So again, we use the model of the car as a particle in equilibrium in the vertical direction, and the model of the car as a particle in uniform circular motion in the horizontal direction. And there's a component of the normal force, as an example, that supplies the centripetal force itself. So this component of the normal force supplies the centripetal force, so the force of static friction. And we can say the angle of the bank is found from tan theta equals to v squared over rg. So this is another equation for you to use when you're working with problems around a banked curve. So the banking angle, again, one thing we can say is independent of the mass. We don't care about the mass, right? If the car rounds the curve at less than the design speed, it's all good. Friction is necessary to keep it from sliding down the bank. But if the car rounds the curve at more than the design speed, friction is necessary to keep it from sliding up the bank. So it means like up and away. Down the bank means that it's going to slide towards the center, right? Depending on the bank. So if you go too slow, as an example, and it's an icy road, you're going to slide this way, right? If you go too fast, as an example, and it's an icy road, you're going to slide this way, away from the bank, okay? All right, here's another example, okay? And this is one that you're going to be given, there's going to be a scenario like this again, okay? So Ferris wheel. So we have the normal and gravitational forces acting in opposite directions at the top and bottom of the path. So imagine a Ferris wheel now. You have a tether, right? You have a tether, and we're talking about constant acceleration. Okay, so this is where you're in constant acceleration. Okay, all these scenarios that we've suggested so far. Okay, constant acceleration, and you're moving in a specific manner. So notice that the velocity vector at the top is going to be different at the velocity vector at the side and the velocity vector at the bottom. Your velocity vector keeps shifting around with the motion of the Ferris wheel, okay? We also know that there is a radius r we have to keep track of as well. So we know that the normal and gravitational forces change, right? And we'll talk about what that is. We can categorize this problem as uniform circular motion because we're moving in a uniform pattern. We're tethered. It's a mechanical motion that we're using, with the addition of gravity. And the child that we see here in the Ferris wheel is the particle. So when we start thinking about the particle model, right, as an example, and figuring out some formula, right, for some of these things, at the bottom of the loop, the upward force, or the normal experienced by the object, is greater than its weight. That's at the bottom of the loop, right? So we feel actually heavier at the bottom than we do at the top. At the top, you actually feel lighter, right? Because what's happening is at the top, you have one motion that's pushing you up and another motion pushing you down, but you also have the circular motion, one component of the circular motion that's also pushing you up. So if I was going to annotate this a little differently, right? Let's suppose you're at the top, right? And you're moving in this direction. So I have a direction this way, right? Well, if I have a vector that goes this way, that's right when I'm at the top, right? Then there's no component that goes this way. But what about when I'm coming towards the top, when my vector is this way, right? So as I'm approaching the top of my vector, there's two lines here. There's energy that goes up, right? Oh God. Energy that goes up, and there's also energy that goes across, right? Because we can always break down a vector into two different components, right? So when you're approaching the top, you have this other component right here that's being added to the normal force. And so what happens is you feel like you're going to fly off, or you're lighter at the top. And similarly, if you're at the bottom, right? And again, remember, if the motion is going this way around the circle, right? So if this is the circle, then at the bottom, as you approach the bottom, right, you have another, let's draw a line. You have another vector that goes this way, right, as an example. And remember that this vector is broken down into two other vectors, right? This component and this component, right? And so what you want to do is you want to take this component here and add it to your gravity, right? So it feels like at the bottom that you're actually heavier, because this component of the vector that's traveling in that same direction is additive, right? So you feel heavier at the bottom and you feel lighter at the top, okay? So that's kind of important to understand, okay? And we have different equations for those things. So let's take a look at some of those equations, while we move forward. Okay, so let's take a look here. So again, we can see that the sum of all forces, example, at the bottom, right, is equal to the normal force at the bottom minus the mass times gravity, which is really equal to the mv squared r, where mass times acceleration, and acceleration is centripetal. Centripetal acceleration is v squared over r, so we can say mv squared over r. When we massage this equation, we can cancel out certain elements. So we have the normal force at the bottom then is equal to mg times 1 plus v squared over rg. Okay, that's the equation we'd want to use. Similarly, at the top, like we said, because you feel lighter at the top, the sum of all forces at the top is equal to the normal force at the top plus mg, right? Which is equal to mv squared over r. And so now you notice that the equation seems different, -1, which means you're going to feel lighter. All right, so that is another type of motion. Okay, here's another one, vertical circular motion, where I have a ball that I'm swinging, right? Let's say in a vertical circular motion, similar to the Ferris wheel example, but I'm swinging it as fast as I can, let's say. If I do this, then we can say that the speed of the ball is not uniform. Why? Because, so up here, this was uniform circular motion because it's a mechanical motion that's happening, right? But here, if I take my arm, if my arm is here in the middle of if I'm swinging the ball, and let's suppose, I'm just going to draw a bad picture of an arm. Let's suppose my arm is here, right? And I'm swinging the ball this way. So here's my hand, right? As an example. And I'm drawing with a mouse. So be kind, guys. Be kind, right? So, you have a tether that goes from here to here, and I'm swinging the ball over and over again. The reason why this can't be consistent or uniform is because at the bottom I tend to accelerate. I accelerate at the bottom and I decelerate as I come to the top. And this acceleration and deceleration makes the motion non-uniform. And so at the top the speed is minimum, and at the bottom the speed is maximum. Try for yourself. Take again another ball and tether it, so hopefully somewhere in open space where you're not going to hit anything or anybody, and then try it out. You're going to notice at the bottom there's more of a swing. And how does this work nicely? Well, think about the game of bowling. This is kind of what we're doing with our arm. When we're bowling, right, we kind of start off at the top. Best bowlers kind of start off at the top of the arc, and as they come down, they let the ball go right at the bottom where it's the most speed, right? And as they do this, right, they have a great amount of energy or momentum, and it can actually project the ball, in the bowling alley very quickly. And the more momentum that you have at the bottom, and accuracy, hopefully, you can get a strike in bowling, right, which is what you want, right? So this idea of bowling, that's how you work. You can cast a ball downwards, right? And that you can use gravity to help you. All right, some additional equation help. So again, at the top, it looks like this. At the bottom, it looks like this. There's two different tensile strengths that we're going to use. So the tension at the top then is mv squared over r minus mg, right? So there's less tension, there's different tension at the top than there is at the bottom. Why there's less tension at the top? Because we're slower at the top, as an example, compared to at the bottom. And notice in this case, we're swinging this way, okay? So at the bottom, at the end of the day, we add mass times gravity. Why? Because it's in the same direction as our motion, right? So it's additive. We're here, it's subtractive. So it feels differently. It's not consistent. The speed is not consistent. All right, so when we think about non-uniform circular motion, then what we just talked about, so the acceleration and force have tangential components, right? So tangent to the curve. Force, the force, across the radial acceleration, if you will, which is this force, sum of all forces in the radial across the radius here, and the sum of all force across the tangent, right? They equate to the force, the sum of all forces in general in the direction of force as a combined vector. All right, so this is what we can say. So sum of all forces equal to the sum of all forces towards the radius and the sum of all forces across the tangent to create the total force. Okay. So radial force towards the middle, tangential force tangent to the curve, which means a perpendicular. Or parallel to the curve. Perpendicular means this way. All right. So one thing we also know in a non-uniform scenario, which is what we talked about, is the gravitational force exerts a tangential force on the object, right? And we can look at the components of Fg. So again, as it's coming down, right, you can see that mass times gravity is pulling down. Your mg cos theta, all right, you can see again that because we're in a circular motion, that cos and the kind of almost like a vertical axis, which would be more like a y-axis. Y again is if we change our axes and you say this is x and this is y, y is related to cos in this scenario because we're modifying our axes. We're in a slope or some kind of curve. And sine is equal to the tangent or horizontal. So this is where that relationship changes again. Okay. So then once we've done that, we've decomposed the components of the force that's coming downwards. As an example, as we're coming down the circle, right? We can say that the tension at any point can be found by using T is equal to mass times gravity, and then in brackets multiplied by v squared over rg plus cos theta. All right, so this equation, and we're getting this. I'm not going to do a large proof of any of these things because that's kind of outside the scope of this course. So you're not going to see proofs for these things, but when we massage the formula, we get to the point where we can calculate the tension as an example, again, as we are pointing towards the origin, right, by using this formula here. So if you ever ask a question about the tension, this is how you do it. And this is in a non-uniform speed scenario. So we talked about this. The top and bottom of the circle is different because the tension at the bottom is maximum. We add 1. The tension at the bottom is minimum, where we subtract 1. And the reason for this is because of the way that non-uniform circular motion works. All right, we're going to talk about this briefly, but it's really kind of out of scope. So I'm going to kind of go through it for a second. One thing we can say is we have something called a fictitious force that results from an accelerated frame of reference. Okay, so what does this mean? So imagine when you're in a car as a passenger. When you're in a car as a passenger, we can say that, right, you are feeling a fictitious force, a force that's pushing you outside of the car, even though you're in this frame of reference. By the way, to give you guys a little bit of context around this, when I was younger, I was in a car with my dad. It was an older car, and the door locks didn't work very great, so the door actually didn't close properly. I was on a highway, and I was making a kind of a left curve, and I was in the passenger seat. And I'm telling you, my life flashed, in front of my eyes as I literally hung on the door when the door opened, as I was going around the curve. I can tell you that fictional force or fictitious force, man, it felt real, and it would for people that are passengers. It feels real because I saw the pavement, and when I was coming around the curve. Luckily, I didn't fall out, but we were going at a high rate of speed. 60 kilometers an hour or more as we were going around that curve. So that's enough to kill yourself for sure. But anyways, if you look at this, we feel the outward force is called centrifugal force, right? And it is the fictitious force due to the centripetal acceleration associated with the car's change in direction. So as we're changing, the real force is going, this way. And because I'm inside as a passenger, the force I'm feeling is equal and opposite of the actual force that's happening. All right, so this is centrifugal force. I'm not going to ask you questions about this in the exam, but it's part of our learning when it comes to the way forces work in the real world. So how you feel as an object inside is different because you're in a different frame of reference. You're inside the frame, right? As opposed to being an observer outside the frame of reference and looking at a passenger as a particle model. There's also something called coriolis force, right? Coriolis force is another force. This is something called an apparent force, right? Which is caused by changing the radial position of an object in rotating coordinate system. All right. So again, if I'm inside the coordinate system itself, I'm inside that frame of reference. Again, it's not really relevant to our work here as game developers, but it's good to know these terms, Coriolis force, as opposed to, and as well as centrifugal force, being in a centrifuge. Okay, I'm going to skip through this because this is all stuff that's not related to us. Okay, let's get to this part, which is the examples piece. And I want to work through some of these examples with you and talk about them with you, and then talk about where they would apply. Okay, so let's think about this. So here's a example, and this is right from the book, right? So a conical pendulum example. All right, so imagine the motion of the ball. So a small ball of mass m, we don't know the mass, is suspended from a string of length L. The ball revolves at the constant speed v, okay, in the horizontal circle of radius r, as shown in figure 6.3. Because this string sweeps out the surface of a cone, the system is known as the conical pendulum, okay? So conceptualize. Imagine the motion of the ball in figure 6.3 and convince yourself that the string sweeps out a cone. We see a cone shape. The ball in figure 6.3, right, does not accelerate vertically. So there's no upward and downward motion. Therefore, we know we can use the monocle as a particle in equilibrium. That's a different scenario, right? And it experiences centripetal acceleration in the horizontal direction only, right? So it is modeled as a particle in uniform circular motion. Okay, why? We are tethered and there's no other motion up or down. Gravity is not a factor because gravity is not acting in the same direction as the direction of motion. Horizontal is not the same direction as gravity. In a vertical circular motion, we can't have a uniform circular motion because on the vertical, gravity takes hold at the top and at the bottom of the motion. Here, we don't have gravity taking hold. It's canceled out because all we really care about is the stuff that's on the horizontal. So we only take the horizontal component of the motion, and we don't care about the vertical component because it doesn't apply. Because we can say that unless we're swinging the ball up and down at the same time. Okay, so that's one thing that's important to understand. All right, so let's take a look at this when we analyze, right? we let theta represent the angle between the string and the vertical, and we come up with, this is the proof that we talked about for the equation that we had previously. I'm just going to bring this in place a little bit. So we can see that this is how we get to v, the velocity is equal to the square root of Lg sine theta tan theta. There's your proof. All right, so we start off with the sum of all forces across the y-axis in equilibrium. We can say that the equation number 1 is T cos theta is equal to mass times gravity, right? And then equation 2 is the sum of all forces across the x-axis is equal to T sine theta, which is equal to mass times centripetal acceleration, which we can convert to mv squared over r. And then we can say that tan theta then, right, is equal to v squared over rg. And we want to solve for v. We move the equation around, and so we get to v is equal to rg tan theta. We know that rg is also can be expressed as Lg sine theta, right? The length times gravity sine theta. And so we can get to this equation here. That's the proof. All right, here's another one. How fast can it spin? Okay, so here's an actual, some actual numbers. A puck of mass 0.5 kilograms is attached to the end of a cord 1.5 meters long. The puck moves in a horizontal circle, right? So we're looking at a top-down view, right? This is not a vertical motion. As shown in figure 6.1, if the cord can withstand a maximum tension of 50 newtons, what is the maximum speed at which the puck can move before the cord breaks? Assume that the string remains horizontal during the motion, so it doesn't go up and down. Okay, so again, just like before, it makes sense that the stronger the cord, the faster the puck, right? And also we can expect a more massive puck to break the string at lower speed because, you know, again, think about whirling a bowling ball instead of a puck instead, okay? So because the puck moves in a circular path, right, and it's on the horizontal, this is the key thing, on the horizontal, not the vertical, right, we can say that it's a particle in uniform circular motion because it's moving across the horizontal, okay? So how fast can it spin? Well, we know we can take that equation that we were given earlier, which is the tension is part of the information we were given. So T is equal to mass times v squared over r. We're incorporating the tension and the centripetal acceleration into Newton's second law, right? And then we want to solve for v. We massage the equation. So we say that the speed is equal to the square root of the tension times the radius over mass. And then what we want to say is that v max, right, is what we're saying, the maximum velocity or maximum speed, because there's no vector here, right, is equal to the square root of the tension times the maximum radius, right? Or sorry, the maximum tension times the radius over mass. And then we sub in the values we know. So again, the maximum tension is 50 newtons times the radius, 1.5 meters. Again, notice that we're keeping the units in the proper order, right? So meters and newtons. And then we get over the mass, which is always in kilograms for us. And so we get a result of 12.2 meters per second. Okay, that is the velocity maximum, or the speed maximum, not velocity. Why? Because anything greater than this is going to break. It's going to produce more force on the tether than it can take. It'll break the tether, and then it'll fly off into oblivion. Okay, so that is how fast it can spin. Here's another equation. What is the maximum speed of the car? Okay, so these are all examples that you may see on your test, and these are all worked out for you here to give you a sense of how to do it. Again, here's the question or the problem. A 1,500 kilogram car is moving on a flat horizontal road. Again, flat horizontal, no bank. Okay. It negotiates a curve as shown in figure 6.4. No problem. If the radius of the curve is 35 meters, so from here to the middle, right? And the coefficient of static friction between the tires and the dry pavement is 0.523. Find the maximum speed that the car can have and still make the turn successfully. Okay. So again, what we want to do is we imagine that the curved roadway is part of a large circle, so that the car is moving in a circular path. Again, what we're having is horizontal motion with nothing to do with gravity in the vertical direction. So we know that the particle is in uniform circular motion, right? Because the vertical, the y, is in equilibrium, right? Because of the normal force. So mass is pulling the car down, but it's not going to pull it through the road because the road would be here, right? So here's the road, right? And actually, let me redo that. Here's the road. Should be at the tires, right? So the tires are here. So mass is pulling down, but the road successfully pushes the car up. So it's not like the car is not going to sink into the road. So we can say that this on the y-axis is in equilibrium. And the only thing we care about is this, because this is the only force that's acting that's not in equilibrium. Okay, so that's what we want to look at. Always look at those forces, right? So we can analyze, and it shows the force in the car. The force that enables the car to remain in a circular path is the force of static friction, this part right here, right? And it's static because no slipping occurs at the point of contact between the road and the tires. And if the force of static friction were zero, for example, if the car were an icy road, the car would continue in a straight line and slide off the curved road, right? Because we wouldn't be able to stay on the road, wouldn't hug the road anymore. Cool, so let's analyze it. So we can say that the maximum speed, or Vmax, the car will have around the curve is the speed at which it is on the verge of skidding outward. At this point, the friction force has its maximum value, so the force of static friction, max, is equal to the coefficient of static friction times the normal force. So we can say that F max, force of static friction max, is equal to the coefficient of static friction times the normal force. And we know that we can break this out into, this is equal to mass times v squared over r, where this is again the centripetal acceleration, right? Centripetal acceleration, v squared over r, because we know that this is all of force, and this part here, the way this is derived is F is equal to ma. So we know that the force of static friction times the normal force is equal to mass times acceleration. We know what the acceleration component is because it's we're accelerating at constant speed, so it's consistent, right? And then the sum of all forces then across the y-axis is in equilibrium. We can say that it's equal to mg. But what about the sum of all forces across the x-axis, or the horizontal? Well, we know that Vmax, if we massage this formula, right? If I want to find the maximum speed, is equal to be the square root of the coefficient of static friction times the normal force times the radius over mass, right? And when we massage this, right, we can break the normal force into mass times gravity, and then we have mass over mass. We can cancel out the mass altogether, so mass doesn't matter. That's why we always say mass doesn't matter in this scenario, right? And we can say that it's equal to the maximum speed is equal to the square root of the coefficient of static friction times gravity times the radius. And now that we have the thing in the proper format, we can sub in the values that we know, which is all of them. And we can say that the coefficient of static friction, 0.523, the gravity, acceleration due to gravity is 9.8 meters per second squared, and 35 meters is the radius of the circle, so that gives us a velocity maximum of 13.4 meters per second. That's how you figure it out. All right, so hopefully it's just the same equations that we're using the same formula, so you understand how that works. Here's another one, riding the Ferris wheel. Okay, so a child of mass m rides on a Ferris wheel as shown in figure 6.6. The child moves in a vertical circle of radius 10 at a constant speed of 3 meters per second. So this is not a non-uniform motion because it's mechanical motion. Okay, this is the thing. So it isn't vertical. We're in a vertical situation, right? But we're not in a non-uniform motion perspective. Why? Because we're mechanical. The mechanical arm is the thing that's moving the Ferris wheel around and around. It's not accelerating as it gets to the bottom. Okay. However, the question here is not how much speed is, but rather determine the force exerted by the seat on the child at the bottom of the ride. So force is something that's going to change because of the directions of, basically as the Ferris wheel moves towards the right and as it approaches the downward motion, the force downward is added to the gravity force, the force of gravity, and so it feels like you're heavier. So we know at the bottom of the ride we're going to feel heavier than at the top. So A asks us, what does it feel like at the bottom of the ride? What's the weight of the child? Weight, right, of the child at the bottom, which is mg. How does that look? So again, we conceptualize. We know that the force, gravitational force on the child act in opposite directions at the top, but it moves in the same direction at the bottom, which means we're going to add forces. So at the bottom, we can say that the equation we're going to use is the sum of all forces is equal to the normal force at the bottom minus the mass times gravity, right, as an example, which is equal to mv squared over r. Again, that mv squared over r is mass times acceleration, and it's centripetal acceleration. We're breaking out into v squared over r, so F then is equal to ma. But we also have other information here, the normal force at the bottom minus gravity, right? And when we massage the equation, we can say that the normal force at the bottom is equal to mass times gravity plus mass times v squared over r. We're adding things together, right? So we brought this over. That's what's happening. Because notice that the way we figured this out is mass times gravity, that goes on the other side of the equation. When I bring a negative over to the other side of the equal sign, it becomes a positive. And now we have the normal force at the bottom is equal to mass times gravity plus mv squared over r. And if we massage this, we get the normal force at the bottom is equal to mg 1 plus v squared over rg. And then so if we sub in the numbers, we get that 3 meters per second squared, which is what we were given up here. We said that the child moves in a vertical circle of radius 10 at a constant speed of 3 meters per second. So 3 meters per second, radius 10, gravity 9.8 meters per second. We get to 1.09 mass times gravity, or we get to a 1.09 G's, we can say. So it feels greater than normal because of the way that the Ferris wheel is pushing down. Feels like the person feels heavier at the bottom, 1.09 mg. And similarly, the second question is what happens when we're at the top? Well, now our equation is slightly different, where at the top is mg minus mv squared over r. And when we massage the equation n top, we can see that it's 1 minus. This is the equation that we're going to get over here, right? So mv squared over r, we can say that is mg 1 minus v squared over rg. We sub in the values that we want. And now we can say that, clearly we can see that it's less than 1g, or 1 gravity, okay? So at the top, we feel lighter. At the bottom, we feel heavier. Mass is different. Or, sorry, mass is the same, but weight, it feels different. Here's another one. Okay, and I'm going through all these because I want to go through them, just walk you through them all, because, you're going to see some of this stuff on your test, and I want you to know how to handle this stuff. And you can always look at the videos, and the PowerPoints are going to be, it's open book, open internet, to help you conceptualize this stuff. It's not supposed to be a hard test. It's a test to help you understand, and so that the stuff goes through your brain when it comes to understanding how physics works. That's really what the outcome of the course is in general. So say, again, a small sphere of mass m is attached to the end of the cord of length r and set into motion of a vertical circle about a fixed point O. Okay? Now, this is different motion because if we know that this is not uniform, because it's not mechanical motion, we don't have a Ferris wheel, we have non-mechanical motion, and we have it in a vertical direction, which means that it's going to speed up as it comes to the top, slow down when it comes to the top and speed up when it comes to the bottom, right? That's how it's going to work. Actually, the motion's in this direction. So it's going to, as we approach the top, it's going to slow down, slow down, slow down, and it's going to speed up at the bottom. And this speeding up and slowing down makes it not uniform, right? So we need to use, we're going to use the model as a sphere, as a particle under a net force in non-uniform circular motion. We can't do that. Can't use the uniform circular motion. It's a different kind of scenario. We're using a particle and a net force, okay, as working on a circular path, right? So that's the answer. That's how we're going to do it. And the way to do that is we analyze the force diagram in figure 6.9. We see that the only forces acting on the sphere are the gravitational force, right? So we can say the sum of all forces, the tensile force is equal to mg sine theta, which is equal to mass times acceleration, the tangential acceleration here, right? So tangential force, we get a relationship with tangential acceleration. We can say that a tangential acceleration, then after we massage everything, is equal to, we can cancel out mass on both sides, where we can say that the tangential acceleration is equal to gravity sine theta, depending on the angle of that particular place in the circle. So what I mean by that is, depending on this angle here, where in the circular motion you are, that will lend itself to different amounts of force. So again, at the top, when you're at kind of a 90-degree angle, that's when you have the least amount of tension, and at the bottom, that's when you have the most amount of tension. And so now you can see that when we massage this, we can say that the sum of all forces across the sum of all radial forces is equal to the tension minus mg cos theta, which is equal to, again, it's a force, so we must have some kind of mass times acceleration, which is mv squared over r. And when we move things around again and we solve for the tension, we can say that the tension force, or the tension itself, is equal to mass times gravity, and again, v squared over rg plus cos theta, and this is how we find the tension, these two things. If we have the numbers that we were given, we can just sub them in, and we can get the total tangential acceleration and the tension on the cord, okay, which are both vector quantities. Whew. So those are all the different scenarios that you might see on the test, and they're broken out for you in terms of how you would break down that problem. Neil says, will it be all math or some theory? Most of it will be math. So the theory you're going to apply to the problem. So you have a problem, and it'll be similar to what we've shown you here. All these examples, that's how the test is created. The test is created to get you to practice some of the examples we've given you, so you understand motion in terms of math, physics. All right, homework for you guys. All right, homework for you guys. And I say homework in terms of practice. How do you practice this stuff, right? So here's some homework. How do you figure this out? So problems number 1. A light string can support a stationary hanging load of 25 kilograms before breaking. Cool. An object of mass m, which is 3 kilograms, is attached to the string, rotates on a frictionless horizontal table in a circular radius of r is equal to 0.8 m meters, right? So 80 centimeters. And the other end of the string is held fixed as in figure 6.1. What range of speeds can the object have before the string breaks? When I say range of speeds, what's the maximum speed that this thing can have? That's what it means. What's Vmax here? Okay, so let's go over it again. What type of motion is this? What kind of circular motion is this? I'm talking about 2 types of motions, circular motions. What type of motion is this one? Come on, guys. I know this is not the most exciting stuff to look at when you're watching stuff. Okay, you got centripetal force. That's for sure. You have a centripetal force. But what else? What type of motion? I'm not saying what type of force it is. What type of motion is this? So you're on a horizontal table, right? It's uniform. Thank you, Sophia. So why? It's because there's no vertical component, right? Again, if we were to draw this out, whenever you get a thing like this, right, and you see that there's none of this. This is being canceled out by this, by the normal force, right? Normal force and the upwards force, the mass, right? That's pulling it down. So this is mg, it's pulling it down this way. And the normal force is pulling it up this way, and it's staying on the table. So we can say that it's the object on the sum of all force across the y-axis is in equilibrium. The only forces that we have then, right, really, when we look at this problem, is there's a force that's going towards the middle of the circle, right? And there's also motion that's going, the tangential component that's going across this way, okay? So what we want to find is how fast can we go before this object flies off the chord, it breaks the chord. That's what we're looking at. Okay, so how fast can it go? Okay. So if that's the case, you have a similar example above. Okay, it's not a conical pendulum, right? Because if it was a conical pendulum, then there would be a tether that would be tethered to this thing like this. Okay, so actually let's redraw that. It'd be kind of like a tether that would be kind of hooking onto the top, and it would be sweeping around in a cone. It's not the case. That is not the scenario. So it's not a conical pendulum at all. All right, so that's the way you categorize stuff based on the things that I've already shown you. If we had a y force, well, we don't have one. We don't know what that would be. But if we had a y force and went up and down, that's a different kind of motion altogether. And it's definitely not it would not be consistent or uniform. That's for sure. Because if we had a y force, the y force itself would be affected by gravity. Somehow, in this scenario, they would go through the table or up above the table. It would kind of hop around the table. If we had some kind of object that would hop around the table, then the motion could not be consistent or constant or uniform. All right, so let's go back to this. So problem number 2. A curve in the road forms part of a horizontal circle. As a car goes around it at a constant speed of 14 meters per second, the total horizontal force on the driver has a magnitude of 130 newtons. What is the total horizontal force on the driver if the speed on the same curve is 18 meters per second instead? Okay, so we're given some information. We're given a rate of speed, 14 meters per second. We're also given the force on a driver at 130 newtons, and we're saying that the curve in the road forms part of a horizontal circle. What type of problem is this? It's motion, around a flat curve of the road, right? We've been given this. There's no bank that's been mentioned, right? But we've been given information about the motion. So we can take this information. We know we can get information about the force of static friction because we know that the force of static friction, the driver is able to, we can calculate that force because we can say that, well, as we go around, the constant force goes around, we know that 14 meters per second, right? We exert this much force. We can figure out the force of static friction by doing that. And once we know, we can figure out, what is the horizontal force based on a higher rate of speed. Next, okay, conical pendulum, right? So this is a clear conical pendulum example. Okay, so consider a conical pendulum with a bob. By the way, this is not the name bob, but it's actually this. The mass is called a bob of mass m, 80 kilograms. That's pretty heavy, right? On a string of length L, 10 meters. So quite a long string. 10 meters is huge. That makes an angle of theta 5 degrees with the vertical. All right, so this is the angle, right? Determine A, the horizontal and vertical components of the force exerted by the string on the pendulum, and B, the radial acceleration. I can tell you guys that one thing that you want to always look at whenever you come to these equations is, and I always ask you this question is, does it make sense? If you get a value that's very small here, 80 kilograms, guys, and 10 meters, right? You got to figure what that means. Does it make sense? Can you work it out can you work out the problem backwards and get the same results? And does that make sense? If it doesn't make sense, then what ends up happening is you're like, you must have miscalculated something, right? So again, we have the information, and what I would do is look back at the pendulum example, right? Which is one of our first examples. And how do you figure that out? Here's your conical pendulum, right? We've been given the equations. So here's our speed, which is the square root of LG sine theta tan theta, right? That's what we've been given. So if you go back to that, and what is it asking you for, right? It says the horizontal and vertical components and the radial acceleration. Those are different questions. Horizontal and vertical components of the force exerted by the string on the pendulum. What are they? Well, it actually breaks it down here as well. So if you go back up to where the first part is, the horizontal and vertical components. Horizontal components is t sine theta, and the vertical components is t cos theta, right? Which is right here. What is t cos theta and t sine theta? Horizontal and vertical components. Okay. Okay. So that's kind of some of those questions. Last one. Okay. A roller coaster car has a mass of 500 kilograms, which makes sense. When fully loaded with passengers, the path of the coaster from its initial point shown in the figure to point B involves only up and down motion as seen by the riders with no motion to the left or right, right? So we don't care about left and right motion. We only care about up and down. So it's consistent. It's a consistent rate of speed, right? Right? So if the vehicle has a speed of 20 meters per second at point A, what is the force exerted by the track on the car at this point, right? And what is the maximum speed of the vehicle can have at point B and still remain on the track? Assume that the roller coaster tracks at point A and B are parts of vertical circles, right, of radius r, 10 meters, and radius, so R1, which is this one, 10 meters, and R2, this one, at 15 meters. So question, what kind of problems are these? Yes. Yes, Neil, that's exactly where it comes from. So what kind of questions are these? There's two parts to this question, right? There's part 1 and part 2. Okay, Sophia says solve for tension max at the bottom and min at the top. Absolutely. And why? Because if you think about this, it's not just tension, but it's asking for what is the maximum speed of the vehicle. The vehicle speed, this is non-uniform circular motion, right? Because the speed increases at the top, at the bottom, and decreases at the top. Speed decreases increase at the bottom and decrease at the top is non-uniform circular motion because you don't have a mechanical. It's not mechanical. Even though you're on rails, right? Even though you're on rails, you will increase the speed. Notice when we go on a roller coaster, it feels like even with the same 20 meters per second speed, we seem to go faster at the bottom and then slow down at the top. Why? Because of this exact example. And this is why roller coasters can be so fun and so scary at the same time. Okay, so that's the example of a roller coaster. So guys, what I would like you to do, again, it doesn't have to be in lab, but I'd like you to try and work out these problems as much as possible because there will be some questions similar to these on your test, 100%. It's going to come. So work out the problem so you have a template. May not be the same, you may not get the same problem. It may be different numbers, but what you want to try and do is use these questions you're going to work out as a template to solve your problems on the test. And I would recommend doing that for each of the questions that I've given you so far to date, right? So create a template for yourself and go, okay, so if I see this kind of question, then I just have to plug in these values, and so that your test can be done within a reasonable time frame. Otherwise, it's going to take you a lot longer to categorize these problems. But these are very common problems that we see in physics all the time. Some kind of roller coaster, some kind of circular motion. We talked about Newton's laws and how they work. All those kinds of things are very similar across most scenarios. No, Patrick, I mean like template, so what you would do is you make your own PowerPoint presentation. So I recommend, right, with all your answers that you vet, right, by doing some research online, right? And this way, when it comes to doing your test, right, you go, okay, that's this one. And then you kind of plug in your numbers and you're done. That's a real great way of doing it, right? Because this test is open book, right? So then I recommend preparing for it, right? As opposed to, and when you're doing the preparation, guys, the great thing about preparing for a test like this, because it's open book and all that kind of stuff, well, I'm also going to give you a sheet of formulas that I'm going to share with you, right, for your test. So next week, expect me to give you a sheet of formulas that you can use for your test. So that way you can kind of look at one sheet and go, okay, I got the sheet and I've got my work that I've done here in my homework. And then what's going to happen is you can use both things to solve your problems so that, you can get it done. By the way, guys, just to let you know, even if we were in person and I was getting you to do this test in person, I would still give you a formula sheet. And in the past, what I've let people do is you get a formula sheet, you can make your own, right? I'm giving you one, you must use mine, but you can write anything you want handwritten on the back of it, anything you want. It just can't be, you can't use different colors. People did really weird stuff. They had, I've had people in the past, they've used things like 3D glasses, and they've written things in blue and different colors, right? So they can look at, I'm not joking around. They've looked at, so they can write over the test over and over again. So they can write in different colors and still see, the thing that they're looking at. Really weird, right? That they've done. People done a lot of really crazy stuff. And I had to say no to that, but they've been really creative people that have come in. People have tried to write stuff down by hand. I said, well, it's got to be handwritten. And then they're like, okay, no problem, handwritten. And then they've gone and photocopied it or scanned it in, right? As an example, micronized it, so scaled it really, really down, right? It was originally written by hand, right? And then they pasted it on their test in a very, very small format, and they brought a magnifying glass. And they said, can I use a magnifying glass on the test? And I'm like, why do you need a magnifying glass? And they said, because I want to look at my answers. You told me to write it down. I wrote it down really, really small. So it was a little insane, and I had to put rules around it. And I had to say, look, you can't write, you can't, kind of scan something in and rescale it. It has to be something that's reasonably scaled so you can see it. You can write small for sure. You can cram stuff in if you want to cram some stuff. And what they did was they did exactly what I'm telling you to do. They took some problems like the roller coaster problem, and they filled in some numbers, and they had some equations next to it, and they put it inside the test. They kind of plotted their basic questions from all the chapters on the test. And then what ended up happening was they had a paper that was completely full of equations and possible solutions that they went into the test with. Plus, they also had my cheat sheet. And I tried to make it as reasonably small as possible so you could fit other things in there. All right. But they had to use my cheat sheet, which I handed out the week before. Okay, so that's kind of how we're doing it now. But this way, you don't need to micronize any work. Just what I recommend is do some of this work ahead of time so that when you hit your test time, you're ready to go. You're prepared, okay, for some of these examples. All right, so that's it for today. I'm not going to cover anything else. So I'm going to give you back some of your time. But again, we can see that up until today, there's only one other thing we're going to cover from next week, which is energy of a system, right? And we're also going to do a short review on the stuff that we've covered already. And that should give you a great idea of what's going to be on the test the following week. Remember, the following week, there's not going to be a lecture. I'm giving you time to do your test during our lecture hour or 2 hours as an example. And this way, you don't have to plot or plan another time frame. However, if you want to, and if Thursday doesn't work out for you, you want to do it earlier in the week or later in the week, I'll let you do it whenever you want. Okay, I'm going to still be here just in case you have issues during your test time. Okay, so next week is the last lecture before the midterm. Okay. Any questions before we go for the day? Okay, guys, thank you so much. We'll see you guys next week, and good luck on your assignment 2. Remember that your assignment 2 is due next week by Friday. If you haven't formed teams already, please do so as soon as possible. and get going. Thanks a lot, Sophia, for all your input. Take care. Have a good week and enjoy your Thanksgiving for those people that are celebrating, guys. Thank you so much. All right, take care. Take care, guys.